In this lecture, we are going to talk about Cauchy sequences in a metric space, and we will use them to characterize what a complete metric space is. So take a moment to pause and read through this definition. And as you do so, I want you to compare it to the definition or any characterization you have of a convergent sequence. All right, so we say that a sequence in a metric space is Cauchy if, for any choice of positive number epsilon greater than 0, there is an index capital N, so that when you grab any two sequence terms whose indices are beyond capital N, which I like to designate with, suppose you have two indices satisfying little m is greater than or equal to little n is greater than or equal to this threshold index capital N, then the pairwise distance between those two sequence terms is smaller than epsilon. So here that's written as d, that's the metric in the metric space, measuring the distance between the mth term and the nth term. That distance is less than epsilon. It sounds a lot like how we describe convergent sequences. In fact, the whole beginning sounds a lot like that. The difference is that at the end, instead of comparing a term in the sequence to a limit, we are comparing terms to each other. So you might wonder, is this really the same idea as that of convergence? And they are related. So let me sketch an illustration of this definition. Imagine here's the first sequence term. I'm just going to imagine sequences of points on this board. So here's the first one, second one, third one, and we go on and on because it's an infinite sequence. But for some very small choice of radius epsilon, I can say that if I've gone out far enough in my sequence, say this is the x sub capital nth term, then all of the points beyond this term are within distance epsilon of each other and also of the capital nth term. So it's like I can imagine some epsilon neighborhood, and all of the terms in my sequence live in the epsilon neighborhood of x sub n and also in each other's epsilon neighborhood. So they're all pairwise close together. So this gives us the feeling that the sequence is kind of clustering up. And when you look at sequences of real numbers, what you probably learned in Real Analysis 1 is that this notion is actually equivalent to that of convergence for sequences of real numbers. So we say on R, the notion of being Cauchy, what we're illustrating here, is equivalent to being convergent. If you're one, you're the other. Turns out that won't be true for every single metric space. So let me step aside. I'm going to erase this picture of a sequence on the board, and we will look at some examples. As I said a moment ago, when you learn about sequences of real numbers in Real Analysis 1, you should have learned that a sequence is convergent if and only if it is Cauchy. If and only if does not hold in a general metric space. So here's the real statement. In any metric space, a convergent sequence is Cauchy, always. The other direction is not always true, but before we discuss this, let's give a quick proof of this first statement. So we would like to prove in any metric space, a convergent sequence is Cauchy. Suppose x sub n converges to x. It's worth noting here that when we write that the limit of a sequence is x, it should exist in the metric space. So if I say this, x is in the metric space. Everything here is happening in the metric space. X is not like outside the metric space, which is an idea that will make more sense in a few minutes. All right, if this is happening, then for any epsilon greater than 0, pick your choice of epsilon, then you can go find some index capital N. So then for any epsilon greater than 0, all right, there exists a threshold index capital N so that normally I write little n, but I'm actually going to write m so that whenever m is greater than or equal to the threshold, the distance from x sub m to x is, normally I would write epsilon if I was just trying to explain the general idea of having a convergent sequence. But the idea is whatever upper bound on my distance I'd like to place here, I could go find an index for it. So actually, we're going to make this bound epsilon over 2. If you're wondering why I wrote m, it's just because I was already using n here. I think I will go back and use n in just a moment. I just didn't want to say x sub n and x sub n. Okay, that was just me. Take a moment to see now if you can finish this proof. This epsilon over 2 should be a clue for how to proceed. To finish the proof, what we would like to do is compare sequence terms to each other. To compare them to each other, we are actually going to go through an intermediary and compare them both to the limit because we know that they're going to get close to the limit. So getting close to the limit is like getting close to each other. All right, formally, let's write that down. Thus, if, and I'm going to say here just two generic indices beyond the threshold. So if little m is greater than or equal to little n is greater than or equal to capital N, so I just mean grab two terms from the infinite tail beyond this threshold, their distance to each other via the triangle inequality is less than or equal to the sum of their distances to the limit. And then we chose this threshold so that these distances are both less than epsilon over 2. And I think we can wrap this up there. We have proven that this convergent sequence is Cauchy by showing that for any epsilon greater than 0, there's a threshold, some fixed point in your sequence, so that when you grab any two terms beyond the threshold, their pairwise distance is less than epsilon. All convergent sequences are always Cauchy. For the other direction, it is not always true. And I'm going to come back and kind of talk through what this second line is saying, and then we will look at examples where this is failing. But before we do so, I want to see if you can kind of detect what's going to happen. So there's a reason why the backwards direction isn't always true. And it has to do with something I pointed out as I was writing this proof. Just take a moment to think, why could a sequence kind of cluster up and be Cauchy and yet fail to converge? And I will come back and talk you through it. When you studied the real number line in Real Analysis 1, you should have had some kind of axiomatic discussion about the fact that R, the real number line, doesn't have any holes. You may have called it the least upper bound property. So something like every set which is bounded above has a least upper bound. The idea there is that the least upper bound exists and it's on R. So there's no like hole beneath all the upper bounds. You could have talked about Dedekind cuts. You may have even approached the fact that R has no holes through the language of like a Cauchy criterion. What all those are really illustrating is that R is a complete metric space. In fact, any Euclidean space Rn is what we call complete. So a metric space is complete when it, like R, doesn't have any holes in it. I'll explain what I mean in just a moment. In fact, let me do it now. When I was writing down this proof, I paused for a second to emphasize that when we say a sequence converges, what it converges to is in the metric space. But not every metric space is as filled in as R is. So you could have sequence terms getting very close together, like in my picture, and they're clustering up. And so it looks like they're trending to something, but that thing that they're trending to doesn't actually belong to the metric space. So what the second line is saying is Cauchy sequences might not converge because maybe our metric space doesn't actually contain what they seem to be clustering to. If it does, so if every Cauchy sequence in a metric space must converge, then this is actually the definition of a complete metric space. So the second line isn't actually a thing to prove. This is a definition. It's like Cauchy doesn't imply convergent unless the metric space is complete. So we are defining a notion on the second line. I think this makes a lot more sense when you see examples. So let me step aside for a moment, finish writing this down if you're doing so, and then I will show you some metric spaces which may not be complete. All right, let's look at some metric spaces which might behave differently than the Euclidean real number line. So the first example says that the metric space is the set of rational numbers equipped with the regular Euclidean metric. So this is kind of like going back over 2,000 years before the existence of irrational numbers. This was the understanding of what numbers look like. So if we throw out all irrational numbers, is this a complete metric space? The answer is no. So let me go ahead and tell you that. But take a moment to try to imagine a Cauchy sequence of rational numbers which does not converge in this metric space. Now, this metric space could be viewed as a subset of R. So if you take your Cauchy sequence and situate it in R, it actually should converge because R is complete. I might be giving away too much here because I would like to give you a moment to think about it, but to come up with a good counterexample or an example illustrating why this is not a complete metric space, try to come up with a Cauchy sequence of rational numbers which actually converges to an irrational number. Because converging to an irrational number on R means not converging in this metric space. Okay, I hope you came up with something. Let me give you two ideas. Again, there's a strategy here for how to create a Cauchy sequence in this metric space which does not converge. Because if you take your Cauchy sequence and put it on R, it will converge. So it's like you need a sequence which is converging to an irrational number. My first example is to take any irrational number, let's take pi, and create a sequence that looks like its decimal expansions. So I'm going to use parentheses for this example. Let the sequence be the sequence of rational numbers 3, 3.1, 3.14, 3.141. I think that's as far as I can go. Each of these terminates after a few decimals and it's 0 afterwards. So all of these like truncated decimal expansions of pi will be rational numbers. And then they're Cauchy because, take any epsilon greater than 0, you can go out far enough in the sequence that the difference in your decimals is so small beyond some point that it's smaller than epsilon. Or maybe I'm overthinking it. You can just say, hey, as we keep writing out terms in the sequence, we are converging to pi, but that doesn't happen in this metric space. So let me write like converges to pi on R. Pi is not a rational number. So while the terms in the sequence cluster up and they get really, really close to each other, what they're getting close to does not exist in this metric space. So this metric space is not complete. You can imagine it like it has holes, basically. Okay, now that you've seen this example, actually, before I move on to the next one, let me give you just another example because I like to remind people about how these terms work. So let me say y sub n. Let this be the sequence here. I'm going to give you a formula for the sequence terms. Those terms look like 1 plus 1 over n to the n. So the first one is 1 plus 1 to the 1, so 2. And then 1 plus 1/2 squared, 1 plus a third cubed. So each of these terms is the sum of two rationals raised to a finite power, like to the 10th power, so rational number times itself. So all of these are rational, but were we to put this sequence on R in a different metric space, we would conclude that it converges to E. E is not a rational number. So while this sequence is Cauchy, it must be Cauchy because it's convergent in R. It's Cauchy in this metric space. It's not converging to a member of the metric space. So this is just another example like this one. So I just wanted to give you both of these because I think once you see them, it helps you kind of create these types of examples. The second space might be easier to construct a sequence in. So here we are looking at in any dimensional space. Maybe I didn't make this clear, but imagine we are working in Rn. So maybe R2, R3, R15. Take the open unit ball around the origin. So maybe it's most helpful to picture R3 and just imagine like the unit ball around the origin. Is this a complete metric space? Try to come to the conclusion on your own. The answer once again is no. This is not a complete metric space. Our approach to thinking of an example of a Cauchy sequence which does not converge in this metric space is going to mirror this one, in that I can take this particular space, the open unit ball around the origin, and I can imagine situating it temporarily inside of Rn. Rn is complete. So if I have a Cauchy sequence in this metric space, it is also Cauchy in Rn, which means it must converge in Rn. So that means if I want to come up with a good example, it has to be one which I imagine converging, but converging outside of this set. How could you converge outside of the open unit ball if you converge to a point which is distance 1 away from the origin? So that's, again, kind of the strategy for how to come up with these examples is to sort of like put them in a different space temporarily where you find what their limit is and you know that the limit doesn't belong to the original space. So it's a bit of a trick. Okay, in this particular case, I'm just going to write down x sub n is, this is might look like a sequence because I'm going to write down an n tuple, but this is like this one, a formula for the nth term in the sequence. Sorry about my sequence notation being a little bit inconsistent. So here, the nth term in my sequence will be 1 minus 1 over n, 0, 0 through 0. So let me note, this is the nth term. Okay. So the first member of my sequence is actually 0. So it's the origin. And then 1 minus a half. So it would be 1/2, 0, 0, 0. Then 2/3, 0, 0, 0. 4/5, 0, 0, 0. If you let n go to infinity, so if you look at the limit of the sequence, it converges to 1, 0, 0, 0, 0, which doesn't belong to this metric space. So this metric space is also not complete. All right. The third example is kind of different because this is not something that you could look at as kind of living inside of Euclidean space. So imagine I take my markers in the room, and this metric space has the discrete metric placed on it. Is this, with the discrete metric, a complete metric space? And I think to answer this question, which I'm going to give you a second to do, try to imagine what a Cauchy sequence of markers would look like. All right, if you were working through the ideas in this example, what I hope that you wrote down is something like this expression, what it would look like to kind of set up the Cauchy inequality. And then you should recognize that there are only two possible distances in a discrete metric space, 0 and 1, which means that unless these terms are the same, this equals 1. So if x sub n is not equal to x sub n. Oh, this marker is ready to retire. Okay. Which means that if I pick an epsilon smaller than 1, which is probably the case, so imagine I pick epsilon to be 1/100th, I am only going to be able to force every pair of terms beyond a threshold to be less than epsilon with each other, to have a pairwise distance less than epsilon, if every single term beyond the threshold is just a repeat of the term at the threshold. Okay, I don't know if I said that well, but I can't have any terms which are distinct beyond the threshold. So that means that a sequence in a discrete metric space is Cauchy if and only if it is eventually constant. But when we talked about convergent sequences in a discrete metric space, we had the exact same description. So a sequence in a discrete metric space is convergent if and only if it's eventually constant. So what we are concluding here is that actually any kind of discrete metric space is complete. So this third example is a complete metric space. Think about why this has to be the case. When we talked about Cauchy sequences, I kept using the word cluster. Like they're clustering up next to each other. They're getting really close together. You can't really cluster with the discrete metric space. So you can't imagine points kind of getting arbitrarily close to each other. The only way for points to be close in a discrete metric space is if they're the same. So there's no ability to kind of squeeze things together when you're working in a discrete metric space. Okay, think through these examples. You're welcome to come up with more examples, especially for the first two. And then when we come back, I have more to talk about. When we talked about convergent sequences, I proved that convergent sequences are bounded. Cauchy sequences are kind of close to convergent sequences, so it shouldn't surprise you that they are also bounded and that the proof is almost exactly the same as the proof that we did before. And then we will also prove the second statement that if you are starting in a complete metric space and you reduce down to a closed subset, then that in its own right is complete. So a moment ago, the second example was the open unit ball in Rn. This would tell us that the closed unit ball would be complete. All right, this is the end of this lesson. So what I would like for you to do is take a moment to play around with both of these ideas. You may be able to prove them right now on your own. I think it's always a good thing to do to try. This first one, if you actually have the proof handy that we did, where we proved that convergent sequences are bounded, see if you can adapt it to this. And then we will work through why the second statement also has to be true. So let me step aside and then we'll come back and do each of these individually. Recall that in a general metric space, the notion of bounded is that you can fix a point, measure distances off of that, and that family of distances is a bounded set. So when we proved that convergent sequences are bounded, what we did was we fixed the limit as the point that we're measuring off of. When we look at Cauchy sequences, we don't necessarily have a limit. But what we can do is like anchor our threshold term and measure off of that. That's going to be the idea is we replace a limit with just a term in the sequence. Here, we are assuming that the sequence is Cauchy. So what I'm going to do is not work with a general sense of any epsilon greater than 0. I'm actually going to pick a fixed epsilon, and I'm going to call that epsilon 1. So actually, let's choose that to be our kind of radius distance. Since xn is Cauchy, okay, I have this little stack of markers here, which I'm about to throw away. Let's see if this one's good. Since xn is Cauchy, this one might also join the pile. Given epsilon equals 1, there exists a threshold index capital N yeah, let me switch. So that all of the terms in the sequence whose indices are at or beyond this threshold are distance 1 from the threshold term. Oh, nice. What this is saying is that beyond the capital Nth term in the threshold, the infinite tail of my sequence, which is most of the sequence, they are all within the open unit ball around this term. That's almost enough. All we have to do now is just kind of manually account for the finite set of terms which arrive in our sequence before the threshold. So this does most of the work for us. Let capital B, this is going to be the bound for the sequence, be the maximum. What I'm doing in this expression is I'm comparing every term in the infinite tail to the threshold term. So now I need to go back and compare how the sequence started each of those terms to the threshold term. So I'm going to say, okay, well, what was the distance from the first term to the threshold term? And what about the second one? All the way through kind of the last one before the threshold. So how about x sub capital N minus 1 through x sub n? Here I'm accounting for the first part of our sequence, and then everything beyond is within distance 1. So that's actually all I have to do here. I don't really need to even justify that this works. By construction, all terms in the sequence are within distance b of our threshold term. So Here, all terms in the sequence are within distance b of the threshold. So in this case, oops, this term here, x sub n, it's like what I sometimes call the anchor point. This is very, very similar to the proof that we did that convergent sequences were bounded. What we had in that proof was the limit appearing here, and here we just have some random term in the sequence. Okay, so I've identified a term, and I'm saying if you measure off of that term, all of the sequence is within distance b of that term. So Cauchy sequences are bounded. Okay, I hope that if you wrote this proof, it was similar. Should follow a similar train of thought. Take a moment to think about this one. And let's see, what are some of the key ideas here? We are essentially beginning in a complete metric space and trying to reduce down to just a closed subset. So if I consider a Cauchy sequence in this closed subset, it is also a Cauchy sequence in a complete metric space. So then it's like, well, if it's Cauchy in the complete metric space, it has to converge in that metric space. You want to conclude that what it converges to has to live in the closed space, and that should start to feel like it's turning into a proof. Take a moment to try to sketch out the argument, and then I will come back and write up probably a pretty short proof. All right, let's finish with this statement. A closed subset of a complete metric space is complete in its own right. Uh, in order to fit the proof here, let me just add some notation. Let's call this closed subset B, and M will be the larger space. All right. Suppose that x sub n is a Cauchy sequence in B. As I said out loud a moment ago, this means that xn is Cauchy in a complete metric space, so it converges. Since x sub n is here I'm trying to say it's a sequence in M, and M is complete, it converges in this metric space. So x sub n converges to x in the metric space. It remains to show that this limit x also belongs to the set B. Let me pause again in case you didn't have a chance to finish the argument. See now if you can do it, now that we've got this start. The idea that you probably arrived at is the idea of an accumulation point. But actually, I want to take a moment to point out that sequential limits are not always accumulation points. If B is a singleton set, so that this is a constant sequence of just the one element living in B, B actually has no accumulation points. So there's a way to handle this. Let me do it. It's basically a two-case argument. The first case is to imagine that X actually appears in the sequence as it would in the illustration, the example I just pointed out. If, let me say, if there exists an index, how about J, so that X equals X sub J, then X is in B by default because X sub J is in B. The sequence was in B. This sentence handles the case that I'm looking at a singleton set, and this is a constant sequence. The constant sequence would converge to its repeated element, but that means that it's automatically in the set. If not, if the limit never appears in the sequence itself, then what you can imagine is that your sequence is getting closer and closer to it in what we often picture as like the traditional way of converging. You kind of imagine this destination that you're moving closer towards. That's definitely an accumulation point. So if not, then for any epsilon greater than 0, the ball of radius epsilon around X intersect, actually also, let me puncture it, just to be really precise, intersect the sequence terms. So here it's like, just consider the sequence terms as a set, is non-empty because our sequence is converging to X. And like here, since X doesn't even appear in the sequence, and when I puncture this neighborhood around it, I have to pick up sequence terms for any epsilon greater than 0. So this is non-empty. So X is an AP of B, really, since this set of points lives in B. As B is closed, that puts X in B. Okay, I wrapped this up kind of fast, but on paper I would write down, as B is a closed set, X is in B. Actually, maybe I just want to put a comma, sorry. I love proofwriting, but sometimes on a board, I use kind of shorthand more than I actually do when I write on paper. Okay, I wrote this proof essentially from scratch without reference to earlier results. But if you look back at our discussion of sequences and closed sets, you will notice that this is essentially repeating a proof that we did in that lesson. And that's because we characterize closed sets by saying that every sequence in them which converges to a limit in the set. So since we know that Xn converges, its limit must be in the set. So if you cited that prior result and didn't write all this out, that's totally fine. All right, that wraps up our discussion of Cauchy sequences and complete metric spaces. Thank you for your attention.